let's explore some basic Haskell. So if I run GHCI, this is the interactive Haskell environment. It will tell me that I'm using some particular version. Prelude here, it says before the prompt what libraries it's loaded, and Prelude is the name for the built-in library in Haskell. So all it's saying is, all we've loaded is the built-in library. And from here I can do some math. I can take 4 plus 4, 4 plus 4 is 8, I can take 15 divided by 3, that's 5. Division desperately wants to be a floating point, so it turned 15 divided by 3 into 5.0. I can do 15 times 3 if I want, etc., etc. And of course, there are lots of functions, like the absolute value function. The absolute value of -4 is 4. Functions looked a little bit different than operators here, in that we put an operator between two numbers, but this is all syntactic sugar. You can also use operators like functions. So I can say plus 4, 4, and that's 8. But the important thing about these functions is that they're a lot more like lambda calculus functions than you may at first realize. So, if I take add and define it as a variable, so I'm taking this function and giving it another name, add, well, add behaves as I expect it to. If I now say add 3, and define that as, well, add 3 is a function, so I can add 3 to 7 and get 10. Functions are curried in that every multi-argument function is actually a series of single-argument functions. So if I add, that's a 2-argument function, but now if I add 3, that's not an incomplete function call, it's a perfectly valid complete function call that just doesn't happen to have gotten quite so far as actually adding yet. To then finish the job, I have to pass in that second argument. That gives us very powerful ways to think about functions, because you can essentially save one of the arguments and then give the other argument later. And that applies to absolutely every function in the language and any function you can write. On top of that, because even these operators are functions, we can do silly things with operators. So I can say, oh, you said x plus y is defined as addition. No, I don't like that. That's too complicated. I want x plus y to just be x. That'll be easier. That'll be mathematically simple. So 1 plus 1 is 1. 1 plus 5 is also 1. 5 plus 1 is 5. This obviously isn't very useful, and you might also think that this breaks referential transparency, because, hey, anywhere that I use the plus function, it should behave the same, right? I had a 1 plus 1 up here somewhere, and it was 2, and now suddenly 1 plus 1 is 1? Well, the critical thing about referential transparency is the reference. This is actually a different plus than any plus we would have used up here. It's a different plus than this plus. So we do keep referential transparency, albeit in a confusing way. Importantly, because this plus is a different plus from the plus up here, my add function still works. So we still do have referential transparency, even though we allow these local redefinitions. By the way, I would highly recommend not redefining plus, because it's hugely confusing. The critical thing is, it's just a name, it's just a function, so if you want to make your own function called plus, you can do that.